pretty fast, but.
Yeah, we're using the V for the same thing that we used ever since chapter
Mhm.
3.
Yeah.
Same V.
Okay, I think it's because we were just going over volume.
Okay, that could mess things up.
Yeah.
Volume should be a capital V, speed is a lowercase v, and so clearly you can tell the difference between uppercase and lowercase v's. So,
If they're next to each other, that looks like a capital V to me. That look like a baby V. That do?
So what is that? I'm confused. What's going on? Like why? What's the difference?
It's supposed to be a lowercase v, and if some people potentially were confusing it with V for volume.
Oh, I thought you said it was volume, or you said it was.
No, that's speed right there. Volume,
Is with the.
when we did density,
numbers.
it's mass divided by volume. I try to make my volume V with the serifs on top, because uppercase and lowercase v's look pretty much the same.
Okay.
For the linear density though, didn't you say something along the lines of like for every meter the string has is the like 0.00133 volume? Or something?
Kilograms, mass.
Oh, so for every meter of string, it's that.
Yep, that's how much mass there is for each meter.
Okay,
For this example,
I see.
that's not universal.
Okay.
Now, I commented earlier that as part of this experiment, you can find the different harmonics by putting a different amount of tension on the string, and from that you can predict what the frequency is. But in my formula right here, there's no frequency. So we need to bring frequency into it. So let's take a look at the classic chapter 2 definition, or chapter 3 definition of speed. How do you find speed?
Distance.
FMA? No,
No,
sorry.
not that one. I heard distance.
Yes, divided by something.
Is it distance divided by time?
It is.
Oh, that's
If you think,
what I said, but
if you talk about if you get pulled over for speeding tickets because you're doing 50 miles per hour, so a distance over time. So it is distance over time.
That is.
I did have it, and I did recently get a speeding ticket. Triggered by this conversation.
I apologize for bringing back the bad memories. So if I'm producing a wave back and forth, so either on the string here or out in the hall, the time it takes to produce a wave is the period. And the distance that it travels in the time it takes me to produce a wave, so that distance right there, and this is a vocab word I mentioned earlier, is known as the wavelength. So it's from some part of a wave, because a wave basically that's the essence of a wave. It starts someplace, it ends up back where it started. These are both waves. For those who have had a little bit of trig, this is a cosine curve and that's a sine curve. For those who haven't had trig, potentially you'll see it at some point. So it doesn't have to be from peak to peak, it could be from trough to trough, or it could be at this point in the curve to the similar point in the next curve. I mean, if it's if we have a constant frequency, then they should all be the same length. Now the symbol that is traditionally used for wavelength is the lambda, which is why I don't use lambda over here for linear density. So if I'm producing a wave, it takes a certain amount of time for me to produce a wave, and how far it goes is the wavelength. Now, this period right here is just 1 over the frequency. This is lambda times 1 over the period, which is lambda times the frequency. And so, or I think I usually write F first, either one. So I can find the speed of a wave generically, any type of repetitive motion wave, such as with a string vibrator here, I have this formula right here. If I'm looking at the speed of a wave traveling down a string, I also have this other formula, and they should be the same speed. So my 121 meters per second should be equal to the frequency times the wavelength. So it's now a matter of, how do you find wavelength? Because if this thing is going up and down 60 times a second, it's not like in a 60th of a second you're going to be able to measure. Well, but we don't have to do it in a 60th of a second. I unplugged it, yeah. Steadily I can hold it. So think about the antinodes there. There we go. At least from this angle, they look bigger. Can you clearly see nodes and antinodes? Because I have a fixed end on both ends, it has to be a node. There has to be a node at a fixed end, because antinode is moving a whole lot. Node not moving at all, so if it's fixed, it's not moving. What I see when I look at it is basically something that kind of looks like that, except better drawn. Something like that, where you've got these nodes here and the antinodes. And in that case, what I just did there were several more of these things. If I think about a wave starting at 0, that's one wave right there. So every 2 antinodes in this demonstration would equal 1 wave. Hopefully that will hold long enough. All right, so right now I'm seeing 4 antinodes. Do you agree?
Isn't it 5?
Let's see if we can. We have
So
1,
the harder
2.
you pull it, is the wider the node goes?
Or the fewer, yes, because there's fewer nodes. If I pull even, I think so.
Harder?
Come on. Don't break on me. Three antinodes. But recognize that I can now measure the wavelength. Let's go to something where I don't have to pull as hard. So 1, 2, 3, I've got 4 antinodes here that I'm seeing. Am I miscounting?
No.
All right. So if I have 4 antinodes, that means I have 2 waves. So one wave starts here and ends here, and the next wave starts here and ends over there. So if I know the distance from the vibrator to my hand, well, I got 2 waves in there. I just divide whatever that full length is by 2, and I have the number of wavelengths. Or, sorry, divide that length by 2, and I have the wavelength. I know the number of waves. And so I can therefore find the wavelength, and therefore I can find the frequency. Now, the actual tension with which I was pulling, I have no idea what that number is. I don't have that level of sense. But in theory, it could be done. Now, I did this when we went into lockdown. It was one of the labs that's usually done at the end of the semester for some of the other classes. And so I did this at home. And I wanted really good results. Two things messed that up. One, the string kept breaking. Probably the most amount of profanity I had to edit out of a video came from filming that one. And also, the camera refresh rate was about 60 hertz. So basically, it catches the rope in one pattern right here, and then a 60th of a second later, the rope's back in the same pattern because it's doing it every 60th of a second. And so, through the camera, it looks like the string's not moving at all. It's not straight. I mean, the string, kind of looks like that, and then that's basically the way it looks.
It's kinda cool.
What's that?
It's kinda cool.
How would I
It
get
was
something-
kind of cool, but if you're wanting someone to actually see nodes and antinodes, yeah, that's not happening.
So how can we do this experiment at home?
You need one of these.
Oh, pretty much.
I'm trying to think of something that has a regular frequency.
Can I borrow that?
What'd you say?
Can I borrow that? You know,
I think people would frown upon that one.
They probably would.
So, anyway. I was able to demonstrate at least the fact that the string was moving by sticking my finger. You're not quite catching it here the way you put them there, but
Oh, that's cool.
you can stick, you hear the extra vibration as it bangs against my finger. So there is some demonstration, whether you see the movement or not, you can have some sense that there's something there. All right. So let's take a look at the harmonics. I'm going to start out with two fixed ends, which is basically what we were demonstrating there. So the simplest pattern in theory, you have a fixed end here and a fixed end here, and you have one antinode in the middle. So one antinode. Two nodes. Now recognize what's happening here. The nodes are not moving. The antinode, this is moving, it is swinging back and forth. It is a constantly repeated destructive and constructive interference. So given what I said, what a wave is, what the full wave looks like, how many waves is this?
One.
Not one.
It's hot, wave.
It is half a wave. Not two, we're looking at waves generally traveling back and forth like that. A full wave, that would be a full wave. So this is a half wave.
Okay.
And there's some distance between them, we'll just call that L. So half of, yep. So that's half a wave, so the length there is half a wavelength. Or the wavelength is just 2 times whatever the distance between the endpoints is. This is the first harmonic. As I reduce some of the tension in the string, take the second harmonic, which is traditionally written like that. That node in the middle should actually be halfway between the two end nodes. How many waves is this?
One.
The one wavelength is equal to L. The second harmonic. They should be of equal size there. How many waves is this?
1.5.
Or the wavelength would be 2/3 of the length between the two end nodes.
So wave got 3 halves on the top.
It's 1.5 waves, and I just wrote it as an improper fraction.
Oh, okay. So that's the first and second harmonic. What's this one, the third one?
Yes, it is. That, need water in it. Questions up to here?
What would people use these for, like, audiologists, like ear stuff, or like what?
The same basic principles here. If you go to see an audiologist, at least for a hearing test, and they play the different frequencies, what's really happening is for the speaker or the headsets or whatever it is, the diaphragm in that is vibrating back and forth at that frequency in order for you to hear it like that. So ultimately, the construction of it. All right, let's take a small little break here. I need to get the props for one fixed, one free end, and I saw the one for the 2 free ends around here. Need to make sure I can grab that. But anyway, we'll take a small little break. I'm just gonna let the camera run because I think I'm more apt to forget to turn it back on than anything horrible is gonna be said while the camera's going. But if you do say something horrible, it will be picked up.
Oh, the multiple choice one?